Welcome to qnawire.
For this problem on the topic of light waves, we have a Young's double slit experiment with white light with the wavelength ranging from 400 to 700 nanometers being sent through the double slits, which have a separation of 0.5 millimeters, and the screen is 50 centimeters away from the slits. There is a hole in the screen at a point that is a millimeter away from the central line, and we want to know which wavelengths will be absent in the light that is coming from the hole and which wavelengths will have a strong intensity there. Now, we know that for zero intensity or for a dark fringe, we have the condition that yn is equal to 2 times the order n plus 1 over 2 times the wavelength lambda n times big D over little d, and n is 0 or any positive integer. Now, this means that rearranging the wavelengths lambda n is equal to 2 over 2n plus 1 times yn times d over capital D, and this is 2 over 2n plus 1, and putting in the values, that's 10 to the minus 3 times 0.5 times 10 to the minus 3, all divided by 0.5. And so this implies that 2 over 2n plus 1 times 10 to the minus 6 meters is equal to 2 over 2n plus 1 times 10 to the power 3 nanometers, or it follows rather. And if we let n equal to 1, then we get the wavelength lambda 1 to be 2 over 3 times 1000 nanometers, which is 667 nanometers, which is in the visible range. If we then let n equal to 2, we get the wavelength lambda 2 to be 2 over 5 times 1000, which gives us the wavelength of 400 nanometers. And so it turns out that light waves of wavelengths 400 nanometers and 667 nanometers will be absent from the light coming out of the hole. Next, for part B, for a strong intensity or bright fringes at the hole, we want yn to be n lambda n times capital D divided by D, which means that the wavelength lambda n is equal to yn capital D over yn times little d over n times capital D. And so if we let n equal to 1, we get lambda 1 to be y1 times d over capital D. Putting in our values, this is 10 to the minus 3 times 0.5 times 10 to the minus 3 over 0.5, which gives an answer of 10 to the minus 6 meters, which is 1000 nanometers. But this is not in the visible range. It doesn't lie between 400 and 700 nanometers. And so we can try n is equal to 2, and n is equal to 2 gives us the wavelength lambda 2 to be, using the same equation above, 500 nanometers, which is within the required range. And it turns out that this is the only wavelength which will have a strong intensity in this range. And so we have lambda equal to 500 nanometers.